All right, we're going to go ahead and get started. Thanks to all of you for joining us today. In this session, we're going to be discussing dust collection system design with a focus on the brains of the system, which of course are the electrical controls. My name is Amy Miller. I'm a training manager here at Donaldson Company. We're going to start off today's webinar by briefly discussing a few fundamental concepts for a dust collection system design. And then we're going to get into collector cleaning methods, which can affect the type of control that we recommend that you specify. You're going to be learning about different ways to control power, interlocks, airflow, differential pressure, and options for specifying electrical control systems. And then we're going to finish up with everyone's favorite part, the Q&A session. Here at Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies, and we excel in producing high-quality filters and equipment. We pride ourselves in having a global reach with a local touch. Our world headquarters is in Bloomington, Minnesota. We have 54 manufacturing plants and 23 distribution centers around the world. As you think of questions throughout the webinar, please type them into the chat box, and our team of specialists will answer them towards the end of the session. And then during the webinar, we might ask you a few questions here and there. You can respond with the reaction emoji, and you can access these by clicking on the little face icon at the bottom of your screen. And with that, I'm pleased to introduce our featured speakers today. Asa Bowen is a product manager here at Donaldson. He started as an applications engineer and a couple years ago transitioned to our product management team, where he specializes in ancillary dust collection system components, including, of course, electrical controls.
I'm happy to be here today. Thank you for joining us.
Thank you, Asa. Next up, we have John Danio. He's a senior key account manager. He leads our strategic team that works with large multinational customers, as well as our OEM team that works with large manufacturers to provide turnkey solutions. He also works closely with engineering firms, and if you have attended a webinar in the past, you'll probably recognize him.
Yeah, good morning or good afternoon, depending on your location. Like Amy said, I've been involved in our monthly webinars for a number of years, and controls is one of our more complex topics, so I'm really looking forward to this one. Thank you.
Awesome. Thank you, John. And also joining us today is Carla Davidson, who is a product manager at Control Assemblies. That's a company based in Plymouth, Minnesota, that we partner with for our custom controls. Carla has worked there for over 7 years and has been in the electronics industry for about 20 years. So Carla is going to be walking us through some of the examples of control panels throughout the webinar today.
Thank you, Amy. Happy to be here. Thanks to all of you for joining us.
Thank you. I should probably mention we do have a few other folks from Control Assemblies on with us as well. They're going to be joining us for the Q&A session. So just to let you know that. And John, why don't you go ahead and kick things off for us?
Yes, thank you, Amy. And as always, we'd like to start out by asking a question about your level of experience. So if you can, please select the reaction emoji that best aligns with your level of experience with specifying electrical controls for dust collection systems. And if you can hit those emojis, get a little feel for the audience. Oh, we got some very experienced, some with a little experience. All right, looks like we got a pretty experienced crew on with us today. That's awesome. Good to know. Thank you. All right, so let's review a few basic concepts about dust collection design. A lot of important reasons, obviously, to control dust, fume, and mist, including safety concerns and hazards, improving air quality for employees, exposure control, reducing potential dust in breathing zones and workers operating the process, environmental concerns. We have EPA standards for outdoor and exhausted environmental air quality and outlet emissions requirements, and cleanliness, the overall cleanliness of the facility. Here's a quick automation of a typical dust collection system. A fan or a blower creates an airflow which is used to capture dirty air with a hood and to convey the material through a series of ducts to the collector. Here the contaminant is separated out, the clean air passes through the filter media to the fan where it's discharged to the atmosphere or back into the facility. And making all this happen is electrical controls, essentially the brains behind the system, communicating with all the main components, including things like the fan, the collector, the cleaning when that occurs, and any sensors that may alert the user if there's an issue, etc. If one component of the dust collection system is poorly designed, the whole system is affected. Here's a real example of a dust collection system. Well, actually two of them next to each other. This is for a welding application that was recently installed. Obviously the weld curtains aren't set up yet, but you kind of get a feel for the setup. You can see the fan at the top with a silencer for noise reduction, the dust collector. These are cartridge collectors, the ductwork, extraction arms with bell mouth hoods at the end of them, and the electrical controls mounted on the wall. When we design a system, a lot of factors to consider. You can see some of them listed here, like the material being collected, the stack pressure losses, future expansion, probably more than you realize. The publication shown here is the Industrial Ventilation Guide, which is written by the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. Guidelines in it are considered by most as the standard for proper ventilation, including OSHA. ACGIH offers multiple week-long courses throughout the year on system design using the Vent Guide as a textbook. If you want to get more into the system design, I recommend you check this out. Okay. There are many different terminologies and formulas we use in dust collection system design. The most basic and widely applied being airflow. The formula is Q equals V times A. Q is the volume of air flowing through the system, often referred to as CFM, cubic feet per minute. To get the airflow, we multiply the velocity of air, which is the measure of linear speed of it for an object, by the area of the hood or duct that the air is flowing through. The formula is one of the basic building blocks of dust collection system design. You really want to have the ideal airflow for moving the particulate through the dust collection. You don't want to have too much or too little, so this is a very important formula to understand. And then we have pressure drop, or delta P, which essentially tells us the condition of the filters as it loads with dust. The difference in stack pressure or resistance between the clean side and the dirty side of the filter. It's measured in inches of water gauge or water column. And finally, we have voltage. We wanted to mention it, that it's really important that you make sure you know the customer's incoming power available when specifying electrical controls, both voltage and if it's a single or three-phase power. It can be very costly and time-consuming to fix it if you don't identify it correctly on the front end. As we start into electrical controls, just a quick reminder, again, as Amy said, to as you think of questions, put them in the chat box and we'll make sure we get to them in detail at the end of the session. So for this session, we're going to assume you've already designed all the main components of the dust collection system, hoods, the ducts, the collector, the fan, over the last few months. And each of our webinars that we've had, we've focused on different areas, so you can go and see those on our on-demand page. Give us a thumbs up if you've ever attended one of those other webinars. I'd like to see if anybody else has found one of those webinars. We can make sure we point you in the right direction. Okay, it looks like quite a few people have, so that's awesome to see. Glad to have some of you back again. For those of you who weren't able to attend, again, you can find those on our on-demand webinar page. If you're looking for trainings on any specific component, or maybe you need help with some of the calculations, you can just scan this code, check them out. We'll post this link again towards the end of the session. When we design a system, one of the last things we do is select the electrical controls. And we're going to hand it over to Asa to tell you more.
Thank you, John. Electrical controls are an important, maybe the most important part of a dust collection system. As the name implies, they monitor and regulate the entire dust collection process to ensure efficient and safe operation, both maximizing performance and minimizing downtime. They can range from very simple to incredibly complex. The controls you're seeing here on the page are much more on the incredibly complex side. Electrical controls are capable of turning the system on and off monitoring and controlling the airflow, running the cleaning system, displaying the differential pressure, which is really important to help understand the condition of the filters, alerting the end user when there's an issue, such as maybe when it's time to change the filters or empty the dustbin. But they can also control ancillary equipment like explosion mitigation devices and allow for remote monitoring of the system. Like I said, controls can range from a very simple, lower cost motor starters in a box up to a much more complex and more expensive and more advanced custom control panels that include ancillary component integration, electronic airflow control, and even more features. Similarly, for dust collectors, they can range from very simple, using a cyclone here that kind of uses mechanical separation to separate dust from an airstream, up to a much more complex medium pressure cleaning system. Typically for these, we're talking large bag houses that would use a separate positive displacement pump to generate compressed air and pulse clean the filters. There's a variety in between that we'll cover today. We often find that with a more simple basic collector, you end up using the more basic types of controls. And similarly, for a more complex collector, you'll use a more complex type of controls. We're going to talk about the 5 main types of cleaning methods and controls we recommend specifying at a minimum, starting with the most basic. Mechanical separation, you might also hear these referred to as cyclone collectors. These use centrifugal force to separate the dust from an airstream. You can see in the diagram on the left that the dirty air comes in the side and is directed through a helix baffle to create a cyclonic spin inside of the collector. The dust particles travel with inertia and impact the inner wall of the cyclone. Consequently, they lose their velocity and will drop out to the cabinet base bin at the bottom. The clean air is not as affected by inertia and won't impact the walls and drop out. So consequently, the clean air will rise up through the middle of that helix baffle and be the clean air outlet through the top of the collector. If the system you designed uses a collector that uses mechanical separation, you're most likely looking at the most basic type of control, which is a motor starter. I do want to take a second to point out that as we go through this, we're kind of talking about the most minimum viable controls that you need to operate each collector. You could have an incredibly advanced control system even for the most simple collector. With remote monitoring, explosion mitigation, there's a number of features you could add, but this is really the minimum. A motor starter is the most simple type of control. It simply operates the fan motor and turns it on and off with a manual buttons or a switch. It's typically going to be located on the collector and will help protect the motor from short circuits and power overloads. Carla, I'm going to pass it over to you to run through the different types of motor starters.
Thank you, Asa. We have 3 general categories of fan blower motor starters. There's a standard motor starter, a soft starter, and a variable frequency drive. So when would you choose just the basic standard motor starter option? When you want the controls to be plain, simple, and cost-effective. Motor starters and manual motor protectors are often referred to as a starter, an across-the-line starter, or a direct online starter. A starter is simply a contactor plus an overload. The contactor will receive a signal from the start button, and it'll close the contacts for the circuit to turn the motor on. The motor immediately runs to full speed. The stop push button is going to open the contactor, which will open the circuit to turn the motor off. And this is the simplest of just on-off control without speed control. The overload device provides a thermal protection. When the motor is drawing excessive current, the wires are going to heat up. The overload protection will open the circuit to protect the wires, which ends up protecting the motor and the equipment. A manual motor protector is another version of a starter. Manual motor protectors will combine the contactor and the overload, as well as adding short circuit protection into one device, and that saves space in the panel. Auxiliary contacts on these starters provide feedback to indicate when the motor is running. Simple motor starters like these are well suited for applications where start-stop operation provides sufficient controls, speed control is not required, and energy savings is not critical. Now those standard motor starters will apply that full voltage to the motor instantly, which can increase the wear and tear on the equipment and increase the peak usage with the bills from the electrical utility. To help reduce that wear and tear on the equipment, a soft starter can be used to ramp the voltage up to full voltage. A soft starter does not control the speed up and down during the operation. It only ramps the voltage while starting and stopping. It does not completely eliminate all of that inrush current, but it does significantly reduce it. We will discuss speed control with variable frequency drives later on. For now, I'll pass it back to Asa.
Thanks, Carla. Here you can see an example of a cyclone collector in an industrial facility with a motor starter affixed right to the base of it. I apologize, this picture is a little bit small, but you probably can see the green and red buttons on that motor starter panel. Those are your on and off buttons that Carla just described. Another very simple type of cleaning method is draining collectors. If you specify a collector for an application that generates mist, think wet machining typically, it will most likely utilize a collector that drains. You can see an example here called the WSO. The dirty air inlet is towards the bottom, on the bottom left. The flow of the air is upwards through the collector through a series of filters. The mist droplets collect on those filters, coalesce into larger droplets, which eventually gravity will pull them down against the airflow and drain them down into a P-trap at the bottom of the collector. Similar to a cyclone, a mist collector that utilizes draining will most likely just have a motor starter. But you also will need some type of gauge to monitor the differential pressure. This tells the operator the condition of the filters. The motor starter can either be mounted on the collector, like we saw in the picture earlier, or it could be mounted somewhere else in the facility and started remotely. Remote starters are often used when the collector is located in a place that is impractical to have a control panel. Think of a collector located outside, especially in the weather we've all been experiencing recently. You would want the controls to be inside the facility and temperature controlled. This is a WSO mist collector, actually 3 of them, that are just in the process of being installed. You can see each collector has both a motor starter, the gray box that's mounted directly to the front of the collector, and 2 differential pressure gauges. You probably see 2 rows of doors on each collector. The bottom row allows access to the primary filter and the top row for the secondary filter. Each gauge will tell you the differential pressure across that filter so you can tell the status of them individually. The next type of cleaning system we'll discuss is a shaker style. These are generally going to be found in intermittent duty collectors. Intermittent duty means that they're often turned on and off as needed because they can't be cleaned while they're in operation. The left-hand diagram, you can see how the dirty air enters in the bottom right and flows upward again through the filters and out the clean air outlet at the top. When in cleaning mode, there's not air moving up through the collector, and the dust is dislodged from the filter surface by shaking the filters. This shaking action might be automatic. It could use a shaker motor like shown here, or it could be manual. Oftentimes this will involve a foot pedal or a hand crank that the operator uses to shake the filters back and forth and dislodge any material. Automatic shaker style collectors, that is the ones that use a motor to shake the filters, will typically need 2 motor starters per collector instead of just 1 like we previously discussed. Since shaker style collectors have a motor for the fan and a motor for the shakers, that's the biggest difference between everything we've discussed so far. Other than that, the same list is the exact same as the mist collector, including the differential pressure gauges that allow you to tell the status of your filters. I do want to take the time to introduce the concept of airflow control. With all the collectors we've discussed so far, it's typically done manually. The static pressure in a system will change over time due to the filters as they age. It's important to consider how you're going to control the airflow when you design a system to ensure that a designed airflow is maintained through this changing of static pressure. As an example, a collector with new filters might have a total system static pressure of 10 inches of water. But as the filters age, as dust accumulates on the filters and isn't able to be pulsed off, that could go up to around 16 inches. Fans can struggle to produce the same airflows at differing static pressures. They operate on a fan curve, so the customer needs to be able to control the airflow to account for those differences. For manual airflow control, the fan needs to have some type of mechanical damper or slide gate, so the operator can manually adjust the area of the duct and therefore the airflow. These dampers typically have a lever that the operator moves to open or close as needed. Building on the example from earlier, immediately following a filter changeout, the damper or gate will probably be closed to a point that maintains the proper airflow because the clean filters have a much lower static pressure. Throughout the life of the filters, the static pressure will increase and the operator will need to adjust the damper as needed to maintain that low level of airflow that keeps dust flowing through the ductwork to the collector. Here is an example of a Unimaster, that is a shaker style collector that was installed on a school wood shop. You can see it's located outdoors. I think there are some explosion protection devices on here as well. And the electrical control panel is not mounted to the collector. In this case, it was mounted remotely on the inside of the building. We recommend that control panels are mounted indoors wherever possible, just to minimize the environmental hazards the controller is exposed to. You can design control panels that are good to negative temperatures and completely waterproof, but if possible, it's going to be easier and cheaper to mount the panel inside. Up next, we have pulse jet cleaning, which is probably the most common type of cleaning method you'd see in a dust collector. As the name implies, these collectors use a compressed air supply to pulse filter bags or cartridges with high pressure air that knocks the dust off and cleans the filters. An example of this pictured here is the DFE cartridge collector. The left image shows an interior view of the airflow. You can follow the gray arrows to see how the dirty air comes in from the top and follows a downward flow. It goes over the top of a set of venturis and the blue items, which are the filters that slide in. The air comes in, moves across the cartridge filter, and the dust or dirt in the airstream is deposited on the outside. The clean air follows the green arrow, moves through the filters, and exits through the bottom of the collector. When enough dust is built up on the filters, this is monitored via a pressure gauge, either digital or analog, a quick cleaning pulse occurs, and the air pulses the dirt off the filters into a collection bin at the bottom. A pulse jet cleaning collector will typically use a basic custom control panel. Essentially, it combines the motor starters with a digital differential pressure reading. This allows the operator to determine set points for cleaning, both high and low. High would be when the cleaning is initiated, and low when the cleaning is stopped. These control panels also allow cleaning while the collector is in operation. But there's also a downtime cleaning option, which would be cleaning once the collector is turned off at the end of a shift. These are a much more integrated solution than the motor starter and gauge that we've discussed previously, and Carla's going to walk you through a little bit more what this may look like.
Thank you, Asa. In the image on the lower right, that's the outside of the panel. This example shows the Delta P Plus downtime controller, which displays that differential pressure and allows you to set the Delta P high and low operational set points for cleaning. Below that Delta P Plus, you find the running pilot light and the start and stop push buttons. That black and red handle is the power disconnect. Moving over to the inside view of the panel, the arrow pointing to the control panel disconnect happens to be pointed at the line side of that fusible disconnect. Please note that the line side voltage of that disconnect will remain live unless the power is also turned off further upstream. The wires you see going down and out of that disconnect are the load side. When the disconnect is in the off position, the load side is disconnected, but the line side could in fact remain live. Below the disconnect is a contactor and an overload, which is the main blower fan starter. In the field, the output of the starter would be connected to the main blower fan motor to provide 480 volts in this example. The rest of the panel does not need 480 volts. So we have a transformer to the left of the disconnect switch, which will transform the AC voltage from 480 volts AC on the primary side down to 120 volts AC on the secondary side. Other control panels may also include a power supply, which will convert the AC voltage to a DC voltage. So transformers are AC in and AC out. Power supplies are AC in and DC out. Underneath the transformer, we see a timer board. This is what the solenoid valves for the pulse jet cleaning equipment connects to. Below that are the strip of terminal blocks for the field device connections. On the back of the door, we see the back of the Delta P Plus and the back side of the pilot lights and start-stop push buttons. So the main feature of this entire control panel is the Donaldson Delta P Plus controller, which was jointly developed as a simple printed circuit board device that monitors and controls the differential pressure in a dust collector, ensuring that the filters are cleaned effectively. It measures the pressure drop across the filters and initiates those cleaning cycles based on the user-defined high and low pressure set points. This helps maintain the optimal filter performance, extends the life, reduces the downtime, and increases efficiency. I'll toss it back to you, Asa.
Thanks, Carla. Here you can see an example of a pulse jet cleaning collector, in this case a DFE, that was recently installed at a weld shop, or a weld school potentially. You can see in the bottom image all the different weld cells with the associated extraction arms. But the collector is located outside, so the controller was not mounted to the collector itself. It was mounted inside the facility remotely. This basic custom control panel, very similar to one Carly just described, it has a digital readout with the ability to set the high and low cleaning set points, trigger alarms if there's any issues, and start-stop the collector from inside the facility. Moving on now to the final and most complicated level of collector cleaning types, we have medium pressure cleaning. This is most commonly used on larger bag houses and almost always round bag houses. Instead of using a facilities compressed air supply line, typically is about 100, 150 PSI, these collectors typically have a medium pressure PD pump located on the ground next to them. The PD pump motor is typically smaller, it's about 10 horsepower or less, and it will create what we call medium pressure compressed air. It's stored in a reservoir tank at the top of the collector and then releases that medium pressure at less than 10 PSI, typically around 7.5. in medium volume pulses every 3 to 8 seconds. The timing of the pulses depends entirely on the arrangement of filters within the collector. Almost all of these collectors will have a logic built in so that the pulse occurs when they are directly over a number of filter bags to ensure the most effective cleaning. The drawing shown in the middle here is a RP collector. The PD pump is circled in red, kind of on the bottom right. It's almost always mounted on the ground because these collectors are rather tall. You can follow the air supply pipe up from that PD pump toward the top of the collector and see where it enters. The other item circled there is that reservoir tank I mentioned just a little bit ago. It's located just above the arm assembly that will spin around a central motor there, and the bags are laid out in a specific arrangement to ensure the pulse is directly down the length of the bag to allow for the most effective cleaning and no wasted air. With the most complicated cleaning method, we are to the most complicated types of controllers. I want to point out again that everything we have shared to this point is really the bare minimum to operate those collectors. You could have a super advanced custom control system on any of the more basic collector types we've discussed, if the application required it, and additional items like ancillary devices or interlocks with other machine equipment were required. In addition to everything we've discussed so far as a feature of a control panel, an advanced custom control panel will typically allow for remote interlocks and the integration of even more ancillary equipment. Interlocks are very common and are set up so the dust or mist collector will turn on or off with a different machine. We most commonly see these with CNC or machining operations where the collector only needs to be running when the CNC is cutting. An advanced control panel typically uses electronic airflow control instead of manual airflow control. And I want to dig into that just a little bit more. Previously, we discussed how you could control the airflow through dampers and slide gates, which is just a lever that you would pull to adjust the amount of obstruction in the airstream. But you can also manage airflow electronically by the use of a variable frequency drive, also called a VFD, along with an airflow controller. These, when working together, will automatically manage the fan motor speed so that the fan is only used as much or as little as is needed for optimum performance. For example, when the filters are getting towards the end of their useful life, the VFD will speed up the fan to overcome the additional static pressure so the system is still performing at its designed airflow. We used to only see VFDs specified for larger systems when this type of technology was a little bit newer to the market. But as costs have come down, we're now seeing them specified on even really small systems. If the budget allows for it, this is the way to go, hands down. The lack of manual intervention from operators on the floor will prevent any issues you would have with airflow later on. When specifying an airflow controller with a VFD, it's important to work with your fan manufacturer to understand the airflow requirements. Often, they will recommend oversizing the fan slightly to allow for the maximum benefits of the VFD. Carla, can you talk us through a little bit more on electronic airflow control?
I sure can. So Donaldson and Control Assemblies jointly developed a simple VFD airflow controller. The image on the right shows the Delta P Plus with an airflow controller as a separate component. The newer touchscreen options combine the cleaning controls and airflow control. Although the user interface may be different between these, the method is the same. Airflow control does require a variable frequency drive to control the speed of the main blower fan motor. And to maintain the ideal airflow, we are using a target range of the static pressure to increase, decrease, or hold the speed steady. Depending on the tap location, that is going to change how this table behaves. The static pressure is going to be either, at the low end, could be decreasing the speed of the VFD or increasing it, depending on how everything is set up. So I don't want you to think that this table is always how every system is set up. It really depends on that tap location and the pressure on the equipment. Depending on the type of equipment in the control panel, the controller may send an analog speed reference to the variable frequency drive, or it could also send a digital signal to increase the speed and a separate digital signal to decrease the speed. So there's quite a few ways to go about this. The drive you see in black is a fairly large example. VFDs for these applications could be as small as 1 horsepower or as large as 600 horsepower. And very common sizes that we see are 10 horse, 30, 50, 75, 100, 150 like the one shown here, and 200 is also pretty common. The VFD controls the speed of the motor, which reduces that inrush current even better than a soft starter. This increases the energy savings from the utility's peak billing. And also when the operating conditions will allow for the motor speed to be reduced to about half of what is needed or 3/4, or just any amount of hertz that's less than full speed, energy savings will be increased compared to a standard motor starter or a soft starter, which operate only at full speed. Next, we'll talk about adding some additional motors and components. Now, if the system has ancillary components, you can specify that they're integrated with the control panel. Explosion mitigation devices like the fire suppression system, isolation valves, explosion vents are incredibly common and can be programmed on the control panel to make sure the system will shut down appropriately if there were to be an event. On that topic, the startup and shutdown sequencing is very important. So here's an example showing the starting and stopping sequence of a collector system with some ancillary components. Here we have a conveyor, a rotary airlock, and the main blower fan. The key is to start with the device that is furthest away from the main blower fan and start them in sequence with time delays in between. We would start the conveyor first, and then the rotary airlock, and then start the main blower fan last. Shutting the equipment down is in the reverse order of the startup sequence. The main blower fan would be the first to stop, and then the rotary airlock, and finally the screw conveyor. Next, we'll look at, the advanced ones. Our most advanced control panel includes a larger touchscreen. This interface is incredibly user-friendly. At a glance, you can very quickly distinguish the status of the ancillary components. Here we have a customized view to show a blower, a positive displacement pump, the manifold, rotary airlock, and a screw conveyor. The differential pressure gauge shows the red zones for the alarm levels, the yellow zones for the warning levels, and the green zone for the main operating level. The cleaning arm of the RP collector is also shown on this home page. And speaking of advanced features, I will kick it over to John next.
Yeah, thank you, Carla. We wanted to mention that many dust collector manufacturers are also offering the ability for operators to monitor their systems remotely. At Donaldson, we have a system called IQ, which essentially makes dust collection systems smart. I mean, we use smartphones and smartwatches and smart TVs, so why not smart collectors? This allows customers to be able to monitor their dust collection systems remotely, which could be for a single collector, a single location, or for larger companies with multiple locations. It provides customers real-time data, alerts when there's an issue, and provides historical reports. As you can imagine, customers find this incredibly useful. It's not always obvious when there's an issue with the dust collection system until there's a major issue. And now production has to shut down in order for maintenance team to come in and fix it. You can also be a challenge to identify the root cause of an issue. So having the data at their fingertips is very useful when it comes to troubleshooting, and also helps with compliance record keeping. So here's what our remote monitoring system can track. Again, most companies are starting to offer this. There's things like differential pressure, airflow, if an operator forgot to turn on the compressed air, if the bin level is getting too full, etc. Again, most manufacturers are offering this, and customers really appreciate it, and it's something to consider when specifying a dust collection system. So now we want to give you a little guidance on where to start in terms of developing an electrical control specification. So we have this little pre-sale checklist that we'll go through here, and Control Assemblies has helped us create a configurator tool that we use when we're building a control panel for a customer. Again, I'm sure most manufacturers have something very similar, but we thought it would be useful to run through the main selection items we have in the tool so you get a better overall idea of where to start. First, you'll need to know the fan horsepower and voltage, which we talked about earlier. Then the fan starter type. Does the customer want a standard starter, which costs less but can be harder on the equipment and may produce higher utility costs on larger horsepower fans? Does the customer want a soft start, which ramps up the fan speed slowly, reducing wear and tear and utility costs? And are you specifying a VFD with or without airflow control? Usually they always have airflow control built into them. The enclosure rating of the box itself, is it NEMA 12? When the control panel is located indoors with more standard temperature and humidity conditions, somewhere between 32 and 90 degrees and up to 85% relative humidity. The NEMA 4 for indoor or outdoor use produces a degree of protection against the elements, or is a control panel in a hazardous location. A class 1 may have flammable gases or vapors present, or class 3, which has combustible dust, where combustible dust may be present. The control type, is it a basic control like the magnetic motor starter, a standard custom control panel like the Delta P we discussed, or a more advanced custom control panel with a touchscreen like the HMI panel? Also, as we move down the list, an additional Are additional gauge required, such as an after filter HEPA? We want to track and monitor that. Are there additional motor starters needed, such as a second motor starter for a shaker style collector? What type of alarms are requested by the customer? Remote starting options, we talked through that quite a bit. Interlocks to the production machine that can control the collector so you can turn it on from the machine. Timer delays, and then a whole list of miscellaneous options such as remote monitoring, emergency stop, a push button, or a fan runtime meter. So design electrical controls for a dust collection system can be complicated. Each system and facility is unique. There's a lot that goes into it, but that's what we're here for. We've sold countless dust collection systems around the world. We have local support in every market, and we're here to help make sure you get it right the first time. We understand that having a reliable local resource to leverage for complex projects is important. And we always have qualified people, not chat bots, that are available to help you. And you can feel free to reach out to us anytime if you need help.
Thank you to John, Asa, Carla. We appreciate all your information. We're going to finish up with a Q&A session. So trainers, you can go ahead and turn your cameras back on now if you'd like to. Just a heads up that everyone who attended will receive an email that includes your professional development hour credit. If you don't get yours, please send us an email. Let us know at training@donaldson.com. And there's a few QR codes if you're interested, including the events page for live upcoming webinars. Our next one is actually in a couple weeks. I think it's on February 10th. And it's going to be focused on combustible dust. So that's a really popular one. You may want to check that one out. And then the on-demand page where we do post recordings of past webinars. So this particular one will be posted as soon as we can get it up there. It usually just takes about a week or two. And in case you aren't aware, we do offer a 5-hour in-person class on system design for engineers that'll be held in select cities across the U.S. We have some upcoming ones. We have Toledo, Chicago, and Minneapolis. They're all coming up this spring and early summer. We are going to post a link. John, would you mind doing that for me? If you're able to access that, we're going to post a link in there to give you more information. Otherwise, you can always send us an email at that training@donaldson.com email if you'd like more information. All right, so here we go. Go ahead and submit your questions. We got some in there, but if you think of some as we're doing this, make sure and let us know, chat it in there. So our first question, is there a standard SCCR for Donaldson equipment?
There is. Typically it's 22K, but if you need higher SCCR ratings, we can do that. I think most of our control panels without much effort can get up to 100 SCCR ratings.
Thank you, Brett. Brad, do you want to introduce yourself since we don't know who you are yet? You can turn your camera on if you want.
Well,
It's up to
that's
you.
okay.
You're like, no.
Yeah, I'm in a cube, so there's people walking by all the time.
Fair
Yeah,
enough.
Brad Blumgren with Control Assemblies, been with them for quite a few years and worked with Donaldson closely for quite a few years. So yeah, I do most of the quoting, some engineering and drafting as well.
Thank you, Brad. Thanks for joining us. All right, so here's our next question. How much of this, this person's probably like, oh my gosh, how much of this is expected to be specified by the design team?
I could take this one. I would say it's as much or as little as you would like. You could, I've seen specifications written that have exactly what they were looking for in an electrical control panel. And those, I'm sure from the control assembly side, are very easy. They can design to a spec. But if you specify the rest of a system, the types of equipment that you have on that system will kind of inform the decisions that are made with the control panel. If you have explosion mitigation devices, put that in the specification. And I know the control assemblies team often deals with specifications that are not written technically, are just saying, here's the equipment we have, we need a control panel that does this, this, and this. So it's not a one-size-fits-all answer. I hope that's satisfactory.
Thank you, Asa. All right, our next question. Can you please explain the difference between the timer board and the pulse cleaning controller?
I'll take this one too. The timer board is directly what will control the pulsing to the collector. And I get why that's confusing because the pulse cleaning controller tells the timer board when to turn on and off. So if you have it set to downtime clean, that is cleaning when your collector turns off, the pulse cleaning controller will detect when the collector is turned off and send a signal to the timer board to start cleaning the collector.
So the timer board's like on the inside of the panel, right? And then the controller is typically on the outside of it?
Both
Sort
of them
of?
would be on the inside. The controller is the one you would have the interface with.
Yeah. I know it is confusing between the two. All right, let me see. Next question. So for fans with VFDs, you use bag static pressure as your feedback and not an actual measure of airflow.
I'll take this. So the static pressure is going to be measured typically in the dirty air plenum and on one side, and then open to atmosphere on the other side. And so folks at Donaldson and Control Assemblies came up with this quite a while ago as a way to not have to add extra devices into the system, because we can control the speed based on the static air pressure and try to maintain a window of a very tight window of that static air pressure without having to grab other devices and put that in to capture the velocity, do some other calculations. On our newer systems, we do have that option if you would like to, but that is a custom solution. If you want to take some readings of the actual CFM or the velocity, you certainly can do that. But as a very cost-effective alternative and a way to just have a simplified solution, it's just simply static pressure from the dirty plenum and meeting the window, if that makes sense.
Thank you, Carla. So the next one, Asa, this is probably for you. Can you touch on the difference between magnahelic and photohelic pressure gauges and the pros and cons of that type that Donaldson offers?
Yeah, that's a really good question. Magnahelic gauges are the most simple. You probably have seen them before. They are just a gauge that will output your differential pressure across the filters. There are two taps, one on the clean side, one on the dirty side, and we're taking the difference to find that value. Photohelic gauges are very similar to magnahelic gauges, except they do have, I believe they're electronic contacts that you can set your set points, both high and low. At Donaldson, we use magnahelic gauges fairly frequently on some of the simpler collectors that we mentioned earlier. We don't really use photohelic gauges anymore. We have phased those out in favor of digital differential pressure readings. We handle a lot more of that, and including the set points on the digital interface, either on the Delta P or the new Contura controller. So we just don't see photohelic pressure gauges used nearly as much anymore. You still could. You can get your set points off of them and you can still operate a collector, but they aren't as common.
Thank you, Asa. All right, our next question. Are your control panels PLC or DDC, or can they support both?
We have a variety of options, actually. So what you saw most often in this presentation was the printed circuit board design, where the interface on the front has a membrane and some buttons. What you didn't see the details of when we were showing the HMI touch screens is that would typically have a PLC behind that for the controls. So there's some solutions that have the printed circuit board design and a membrane. There's another solution that has a programmable logic controller and a human machine interface. And there's an even newer solution that is a more cost-effective version to have a touch screen combined with a printed circuit board. So there's a lot of different varieties available, and then also we do receive requests for specific brands when it is a PLC. So we do have the program ready and available in case there is an end user that would specifically like their PLC to be communicating on their Profinet. We would intentionally make that a Siemens PLC in that case. And there's other things where if your end customer requires to connect to their SCADA system, things like that, we can help make those connections. We could create their SCADA system, but we can also just help them connect the PLC to their SCADA system.
Thank you,
That's all I have
Carla.
on that. Thanks.
Appreciate it. Who typically determines the hazardous zones for electrical installation?
Who is a good question. It is determined by the environmental hazards, obviously, but if a dust hazard analysis or DHA is conducted, oftentimes the company providing the DHA will include some analysis on the hazardous zones. Otherwise, it is kind of up to the process owner and the person specifying to ensure that the hazardous zone is accurate. If you need assistance with this, I know our sales team frequently will go out to sites to determine what the hazardous zones are and what is appropriate to spec out for an electrical installation, but it's not a one-size-fits-all answer.
Thank you, Asa. Next question, what would be the benefit of a VFD without an airflow controller? Would you ever see that or recommend that?
I think we talked about this yesterday, Asa, there really isn't much benefit of a VFD without airflow control, right?
No, you could certainly add additional VFDs to the panel if you wanted the screw conveyor to be on a VFD, for example. But for the main blower fan, if that's going to have a VFD on it, then
You want airflow.
then you're definitely going to want to utilize the airflow controller.
Thank you. Next question, do all the Donaldson control panels meet the requirements of UL 508A?
That is correct.
Quick answer, thank you. All right. And the last comment was just
I'm
a
good
hey,
at
thanks,
those.
appreciate it.
Yep.
All right, we'll give you maybe just another minute to see if anyone is still typing a question. Otherwise, thanks to everyone for attending today. We'll make sure and send your certificate. Thanks for posting those links in there, John. Appreciate that. We have a comment that says VFDs also assist with balancing. Very true. Thank you. Good point. And we will get this recording available on the website as soon as possible. There is one on electrical controls that's up there currently that we did last year. So you can, there's that one. And then this one will be replacing that as soon as we're able to put it on there. With that, we appreciate you coming today. Have a great rest of your day. And thanks to all of our trainers today. Great job, guys.
Yep. Thank you.
Thank
Thank
you.
you.
Thank you.